Hi, I'm Professor Melko, PhD chemist, and today we're going to be doing some practice problems on significant figures, how to add and subtract them, how to multiply and divide them, and scientific notation. So if you're not familiar with these concepts, go back and watch my previous videos. Otherwise, let's jump into the examples. So let's start with the first one here, just a basic. How many significant figures are there in the measurement 0.0024 seconds? You can pause the video here and try to answer for yourself. I'm going to proceed and work it out. So our review of scientific figures, or significant figures, I should say, told us that leading zeros like this are never significant. Okay, so in 0.0024 seconds, these zeros are not significant. I start counting significance at the first non-zero digit, the 2, and the numbers after that are going to be significant. So here there's a total of 2 significant figures. It's just that easy. Now let's get into something a little more complicated. How do I keep track of these significant figures when I add and subtract various measurements? So here I've made 3 different mass measurements, maybe on 3 different types of balances with 3 different levels of precision or uncertainty. And now I want to add all these up. 0.7 grams, 0.41 grams, and 0.575 grams. You can add this up sort of in your head or on the fly, or use a calculator. I have here, of course, the best calculator, TI-83 Plus. Unequivocally my favorite. 0.7 plus 0.41 plus 0.575. I get a final value down here of 1.685 grams. Okay, so you can see I've written this out to the thousandth place, but now I need to decide where do I sort of round off this number. And for addition subtraction, the rule is as follows. We round off this number to the decimal place that is the least number of decimal places in the things we added or subtracted together. So here in the first measurement, 0.7, only to the 10th place. The second one's to the 100th. The third one is to the 1000th. The least of these is the 10th place, right? So there's only 1 decimal point here. So this is the number here that determines in my final answer how many decimal places I can go out to, right? So I have to round this final answer off after this first decimal place. Of course, I consult the next figure here, which is non-significant. If it's 5 or above, then I round up the previous number. So here my final answer here should be 1.7 grams, rounded to 2 sig figs. Because it can only go to the first decimal place, because that's the least number of decimal places, right? And this is the rule for addition and subtraction, right? There's no way we can write this final answer out to all these decimal places, because that implies we know out to the thousandth place, and we didn't know the thousandth place in this first measurement. So that's the rule, and that's the reason for the rule. The answer here should be 1.7 grams. Now, confusingly, the rule is different if you're multiplying, dividing things. Okay, addition, subtraction, we thought decimal places, that's the rule. But for multiplication and division, we instead count up the significant figures in the items that we're multiplying or dividing together. So here I'm going to count the significant figures. They're all significant, 4 sig figs. Here, 3 sig figs. So in my final answer, I'm going to have to report this to the lesser of these 2 numbers, 3 sig figs. So I already know in my final answer there should only be 3 significant figures. Let's go ahead and multiply these things together. 2.109 times 1.25. And I get 2.63625. The units, of course, also multiply together. Centimeters times centimeters gives me centimeters squared. So now I round this thing off to 3 significant figures, meaning I have to round after this 3. I look to the next digit, it's 5 or greater, so I round up this previous number. So to 3 significant figures, my final answer should be 2.64 square centimeters. Okay, so that's multiplication and division, different than addition, subtraction for governing the significant figures. Let's move on to powers of 10 and scientific notation. Scientific notation is how scientists express measurements and numbers. And a lot of times in chemistry especially, we're dealing with really, really tiny things like atoms. And so you don't want to write out all these zeros in front of a number, you want to express it in shorthand. That's scientific notation. And scientific notation depends on us understanding powers of 10. Okay, this was a previous video as well, so you can go back and watch these concepts. For now, let's just jump into this practice problem. Write the following numbers as powers of 10. Okay, our rule is the exponent here is positive for numbers that are large or numbers that have a lot of zeros after them. Our exponent is negative if they're decimal place numbers like this and have zeros before them. So I know for 0.1, this is going to be a negative exponent. And how many, or what value goes up here? Well, it depends on how many places I have to move the decimal place to get it in front of the first number. 1, so it should be 10 to the negative 1. That is the power of 10. That is equivalent to 0.1. The other shortcut here is you can look at how many zeros are before the 1. There's 1 0 here, so I know it should be to the negative first power. Okay. Likewise, how many zeros are after it? 1, 2, 3, 4, 5. It should be to the positive power of 5 because there's 5 zeros after it. So here the answer is 10 to the 5th. Again, you can count out these decimal places. Implied the decimal point is here. You have to move it 1, 2, 3, 4, 5 places. That's another way you can get this exponent of 10 to the 5. So that's the first two here, 10 to the negative 1 and 10 to the 5th. We can ask these questions in the opposite manner. Write out the long form of these numbers given 10 to the 3rd or 10 cubed. This positive 3 means there's zeros after the 1 and there's 3 of them. So this is 1,000. 10 to the negative 8, this negative number means it's going to be a small number with zeros before the decimal point, and there's going to be 8 zeros before I write the 1. So I'm going to write out 3, 4, 5, 6, 7, 8, and then my 1, and the decimal place always goes before that second figure here, that second digit. So 0.000000001. That's 10 to the negative 8. And you can always check your answer here to figure out how many places you have to move the decimal place to get back to this sort of number. So that's the examples of powers of 10. Let's move on and discuss an example of scientific notation. Here we have 3 different problems. Write the following in correct scientific notation. And you remember from the previous videos that scientific notation, you take the number of significant figures, write out your numbers. In scientific notation, after the first significant figure, you put the decimal place, times 10 to the n, where n is the exponent in the power of 10. So how would I write 17.245? Well, assuming all of these are significant, I'm going to write it in this manner. I'm going to write 1.7245 times 10 to the n, and I got to fill in this number n here. What is n? Well, n is the number of places I have to move this. If I have to move it to the left, it's a positive number. So I have to move it to the left 1 place. That means this is a positive 1. So 1.7245 times 10 to the first power is the answer for the first one. And just to check, you can sort of calculate out or do in your head, 1.7 times 10 is 17, so that looks right. Just have that sort of check at the end of the problem. So this would be the first answer. The second answer, these leading zeros are not significant. These trailing zeros are significant because they're after a decimal place. And so the significant figures here are the 6 and the zeros that follow. So for scientific notation, I'm going to write 6.000, always in this format with the decimal after the first significant figure, times 10 to some power, and now you have to fill in what is that power. I have to move the decimal place to the right, so it's going to be negative. Before I was moving it to the left, so it was positive. Here I have to move it to the right, and I have to move it 1, 2, 3, 4, 5, 6, 7 places, so this is a negative 7. 6.000 times 10 to the negative 7 power. The last one here is a little tricky because it looks like it's already in scientific notation, but it's not, right? Our decimal place has to be after the first significant figure, and it's not, it's before. Okay, This leading 0 is not significant. All these other digits are. So I know my final answer here, it should be 2.30 times 10 to some power. So you can try to remember which way you have to move the decimal place, or I would just encourage you to calculate it out on your calculator if you have one around. If you enter this into your calculator, right, you can think about what this number is actually looking like as a real number. This -5 means you have to move the decimal places 5 units. So this is the number here written out in whole form. And now that I have it in this form, I can think about where do I have to move the decimal place to get it to 2.3. I have to move it 1, 2, 3, 4, 5, 6. And I'm moving it to the right, so this should be a -6. 2.30 times 10 to the -6. Just like up here, moving the decimal to the right was more negative. Here I have to move this decimal place 1 unit to the right, so this gets 1 more negative. That's another way you can think about this problem. So the final answer here for this last one is 2.30 times 10 to the -6. That does it for the examples today on significant figures, powers of 10, and scientific notation. You can subscribe to my channel on YouTube. You can catch my weekly office hours on Twitch and go back and watch the previous videos on these concepts. See you next time.